This is going to be the GPU lecture. As you can see from the acknowledgements here on the slide, there are a lot of different pieces that some of this has been stitched together. So the visual language is a little bit Frankenstein, but the material is fairly coherent, I think. Okay. So step one. Yeah, go away. Thank you. Thank you. No. There we go. Actually, that reminds me of an amusing aside. We had a faculty candidate talk recently on last Friday, and the bulb on the projector had burned out. Candidate didn't mind so much because we still had the two LCD projector screens, and also the candidate couldn't actually see any of them anyway because he's legally blind. So we were the only ones who needed to care whether or not it was a big picture or a small one. Okay, so why do we want GPU accelerated computing? Because you could get order of magnitude performance improvement. You could get, and this is, oh, okay, I am going to switch to my other clicker because the laser pointer and that's not working too well. And we can also get, and we'll do a lecture on why this is so important, an enormous amount of energy efficiency. Right. So one of the things that you'll find out if you dig into GPUs is that the energy per operation is substantially lower than the energy per operation on your CPU. And when you become power and or energy constrained, that actually is a determiner of performance. Right. To be able to do things efficiently is ultimately to be able to do things at all in the world that we're currently living in. Okay, so why don't we run everything on GPUs? Because there's this if there. If you can figure out how to actually map your code to the GPU correctly or efficiently in the first place, it will turn out that GPUs only offer this for certain types of code. Certain types of code, this number is much larger, and this number is larger. But if you just took a random piece of code, say you took the LLVM compiler and you wanted to run it on a GPU, it's going to be mostly garbage. Right? It's not going to be particularly efficient. It is not going to give you enormous amounts of speed up. It's not going to make good use of that hardware. Right? So assuming you can find tasks that work like this, it's great. Right? And of course, the other thing that should be running through the back of your mind when you see anyone giving you a promotional slide like this is to think about Amdahl's law. So if you're only offloading 80% of your runtime, even if that particular portion got 10x or 100x speed up, right, you know that you can't get more than a 5x speed up for your whole application, right? Because 20% of it's still running over here. Right, so there's actually an entire line of work that has looked at if I am going to accept living in a heterogeneous computing environment where we have both CPUs and GPUs. And again, that may seem like a bizarre question to even be asking. But I assure you, up until around 2008, this was not a settled question. Right? There are certainly people who, up until about really 2008, still thought that they'd find a way to have the CPUs do everything and finally banish these pesky accelerators. You know, it didn't turn out that way. But there is an entire line of research looking at if you are going to take all the parts that have this sort of structure of parallelism and take them out, do I want to redesign for a different common case than I used to? When the common case was all of these pieces together. So that's a worthwhile thing to think about as well. So if you do not have a compute intensive function, you don't have something that has lots of data level and other sort of structured parallelism, you're not going to be able to take advantage of, but if you can, great. And we've done a lot of really good things with GPUs. So as you saw from the top 500 chart on Thursday, right? Almost every one of these high performance machines that's beating the snot of the Lin pack is doing so with the help of GPU enabled computers. All right. So again, GPUs are serious computers now. They didn't used to be. And even so right now we just call them GPUs. We used to call them GPUs, and in between there was this awkward middle time where we called them GPUs, general purpose GPUs, right? Back before every GPU was a general purpose GPU. Right. So I had a friend who was working with Pat Hanrahan at Stanford in the mid 2000s. And he had a fun story about an ATI product at the time where he was trying to do a barrier, and it turned out that only 15 of the 16 lanes actually worked. So if you executed the barrier functionality, you had to hard reboot the machine. So they learned to not do that. Other fun things, 3 mod 3 was sometimes 0 and sometimes 3. It was not IEEE 754 compliant at the time. So the move to becoming a serious computer had there were some growing pains when you were finally using these things for anything other than, making pretty polygons explode when the robots smacked each other, right? But we have since done so. Okay, so we're gonna briefly review some of the SIMD roots that these things are actually exploiting. They don't actually use SIMD. We'll get to that in a bit. But I want you to contextualize where these things are coming from, right? So all models are useful. Sorry. All models are wrong. Some models are useful. Let's say that one again. It's not the case that all models are useful. So this is a very old but still useful model, right? It doesn't capture the full complexity of even the machines necessarily at the time, but it's a useful way of viewing the world to think about single instruction with single data, single instruction and multiple data, right? Which we talked about with array processors and vector processors. Multiple instructions on a single data, which is a very weird way to look at the world, but there are a couple of things, if you squint hard enough, you can push them in there. And MIMD, which is basically what we just talked about, right? Multiprocessing is very classically MIMD, right? So my parallelism is coming from multiple independent instructions operating on multiple independent pieces of data. And SIMD machines turn out to be really good at data parallelism, right? So we spent the first chunk of this class, really squeezing instruction level parallelism out of things, and finished that off really with SMT, turning TLP into ILP, right? Everything that we built was an ILP engine, other than a brief foray for one lecture into SIMD. And it will turn out that the types of problems that GPUs are going to excel at are these same data parallel problems that SIMD was very good at, right? So even though you may hear that GPUs are using tens of thousands of threads, and technically they are, the type of parallelism that they are using really only matches the case where I would have done very well on a SIMD machine. So don't worry, we'll come back to it. We'll come back to how NVIDIA turns SIMD into SIMT in their nomenclature. Okay. So vector processors with basically one instruction and then cross a whole bunch of data. GPUs are going to do something similar, but subtly different. So again, I know it's been the other side of spring break, and you've purged many things from your brains. I'm just wanting you to page this back in out of wherever you were storing all those margaritas. Okay. Now, recall the other problem of vector processors, right? A vector of adds, it's clear what I want to do. A vector of branches is effectively nonsensical, right? Because if I only have one thread of control, I can't go a bunch of different places, right? And so this is the challenge that GPUs are to a great degree going to ultimately address. But we don't get there immediately. We don't immediately go from vector machines to supercomputing GPUs. There's some steps that happen in between and a bit of wandering in the desert before we get there. So I want to briefly touch on a couple of different antecedents, and to also note that the G and GPU did actually used to stand for graphics, right? So there are going to be, if you've ever poked around a GPU memory system, some leftovers from when its primary and really sole use was graphics acceleration that are still there. So for instance, they still tend to have a read-only texture memory because textures are large and textures are read-only. So I can optimize it accordingly because again, read-only sharing, all sorts of fun stuff is easy. So we're going to briefly look at a couple of things that if you combine them with the history of high-performance vector processing, helps you understand how we got GPUs, even though these were not designed as GPUs. Right? These were coming out of groups of people who eventually worked in the GPU space, but were not thinking that this was going to have anything to do with GPU at the time. So first thing I'm going to talk about is the vector thread architecture. And the vector thread architecture actually was originally designed for energy efficient embedded processing. Okay. But it was very specifically designed to deal with that what does a vector of branches mean question. Right. So they really wanted to, I mean, these are their slides, so they didn't want to say they unified the vector and multi-threaded execution models. I think it's a little bit markety. They came up with a new execution model that in the common case looks like a vector architecture. Right, so I'm going to dispatch the same code to a bunch of cores, vector style, right, as if every core is a lane. But I am going to semantically allow each of these cores to behave as if it is an independent thread. Right, so basically imagine I've got a set of different cores which believe they have their own thread sequencer, but actually have a common fetch engine for the common case where the threads are in sync. Right, so if I have a bunch of code, the code all runs, the code all branches, the branches all go in whatever, maybe they all go the same way. Then I just continue issuing more vector operations. That's very efficient. One dispatch, lots of cores execute stuff, lots of parallelism. But because the semantics of this model are that every one of these cores is actually executing an independent thread, a vector of branches is actually perfectly meaningful. A vector of branches is just my n different cores got to a branch at the same time, and they all went whatever way they went. Now, the good news is if I have a vector of just branches, there are only two possible places they could have gone. Right, so I'm basically just splitting my cores into two sets at that point. Right? If it's a vector computed jumps, it's a little more complicated. They're going to completely diverge potentially, right? And so you can basically then deal with that divergence without breaking your ISA. Right? I don't have to do everything in predication. I can just have some of these cores not execute the same following instruction after a branch. So all those that did, right, I masked that out. You guys go there. The rest of you go fetch something else. Okay, so that was basically the idea, right? So you're combining this sort of vector and thread fetch unit. They had this notion of they call it an AIB, which is sort of the block way to amortize some of these fetch costs. But again, I think I want you to really take away from this is this was originally designed, as I said, for an embedded processor. Right? This was not a high performance, supercomputing accelerator. This was a, ultra low power, super efficient, low energy per operation device. They were trying to get efficiency out of virtualizing these vector operations where there were large amounts of data level parallelism to play with. Right? And they hadn't really done anything truly fancy on the memory system at the time, but this model of control is going to be adopted, right? So you look at a system that works well when it is running mostly SIMD, but has a ISA semantics model that allows it to deal with divergence, right? To have different things happen to different lanes and not have to fix it all in software. The hardware, right, can manage these divergences through the, basically virtualization of what is actually a vector processor as if it was running a bunch of independent threads. Right, so they push that to hardware, and that's basically the idea that it's going to have. Okay. Yeah, so abstract instruction blocks. Again, this is just some amortization about fetch. Again, this was not designed as a sort of massive multiprocessor of a bunch of these, because this is a small, low-level version. But this is actually, to a great degree, the inspiration for what's happening inside one core in a GPU. Okay. The other thing that really inspired GPUs to a great degree, although was also very different from GPUs in terms of where it's coming around. This is late 90s, early 2000s here, were streaming processors. So these are different beasts entirely. The only one of these you've probably ever heard of, you've probably heard of the PS3, which had the Cell broadband engine in it. And that was designed as a streaming multiprocessor. That was a pain in the butt to program. But Imagine and Merrimack are sort of the, this is sort of the small scale, and then this is for supercomputing, better known in academia. And the key thing that they were thinking about at the same time that folks were looking at this vector thread model for efficiency of operation, they were looking at problems in memory scaling. Right? And it will come as no great surprise that the same guy who put together that slide with, one floating point, distance traveled on a wire, was the same guy behind some of these works, looking to optimize bandwidth, energy, data movement. So these are architectures in which data movement is explicit. The original versions of these did not use caching at all. They used scratch pads of various sizes, a very, very, very large register file, and explicit movement between different levels of the memory hierarchy, right? Bandwidth is precious, data movement is precious, so we can't let it go unmanaged. This is basically the mantra that these stream processors are working on. And the way that this then worked, because you did not program these in the same way that you programmed general purpose processors, was you wanted to construct a set of communicating kernels, each of which had their own fully private, fully explicitly managed memory stack, and then a means of communicating records to other kernels that would then process them. All right, so this is where you get something very much like the Cell broadband engine, where you've got a fairly standard IBM PowerPC core, then talk to these 8 SPE units, each of which just had its own local memory, no caching, and had to have that marshaled and returned in a software managed fashion to dispatch across those 8 cores. Okay, so you got specialized languages that come out of that, things like Brook. Again, why haven't you heard about languages like Brook? Because, well, GPUs came around, ate all the lunch of all these things together, and everyone programs in CUDA now, right? So, we have better ideas. But again, if you want to map this to other things you've seen, think about a sort of heterogeneous MPI model between the different communicating kernels, and then even within a single kernel, the explicit management of its memory hierarchy looks a bit different. They did eventually relent and decide that caches might be useful for something, but it was 20 years ago. People had ideas. Okay, so again, if you want to sort of get a focus on what they were thinking about, so this is Imagine, right? Lots and lots of functional units, right? These clusters of ALU, often actually working in a again vector or data parallel model. A very, very large streaming register file. In fact, you actually had a register file hierarchy instead of a memory hierarchy. Right? But again, all of that was explicitly managed. Right? These were all named locations that you explicitly moved data to and between. And then again, Imagine was the earlier smaller version. Merrimack had a much deeper hierarchy. And then you had lots and lots of these processors communicating together. But this gives you an idea. Picture I'm mostly concerned about here. Right? This is why they were trying to redesign everything. Right? So if you look here, where I talk about again, 20 years ago, right? Actually, more than 20 years ago well, 20-ish years ago for Imagine. Depends on where you're talking about the actual chip they built or the initial design. Because those take a few years. So you're looking here, 217 gigabytes a second, right? Versus 1.6 out here, right? Well, those absolute numbers have changed quite a bit over the last couple of decades, right? These are in terabytes, and these are, looking a lot more like this, right? that general shape remains valid, right? The further away I go from the actual thing doing the actual computation, right? The lower my bandwidth is, the more energy it's taking to move data, right? If energy and data movement are my most constrained resources, this is how I have to organize my design for maximum efficiency. Okay, so we bring all these things together and we get something operating on a CMPEN. It's basically the GPU version of the vector thread architecture, a little different because they're optimizing for some different things. And then attached to a memory system that bears a lot of its ancestry from things like the streaming multiprocessors rather than traditional caching. Okay. So one thing to remember is that, well, there is a lot of movement on this in the last few years. GPUs began their life as a specialized accelerator device that first, only a very few people actually needed it all. You used to be able to buy a machine without a GPU in it, right? If you had an old monochrome display, 80 by 50 TTY, you did not have and did not need a GPU, right? And so some of the early development of this really was for, dedicated custom computer graphics, but sure, by a little later on, every personal computer, wanted to be able to push some polygons and rasterize some stuff. And so GPUs became ubiquitous, but they were still very special purpose, and they were treated just like any other peripheral. They're sitting on the other side of your I/O bus, and you don't really share much. Eventually, we sort of realized that what the GPU was doing to do all the graphics computations was linear algebra. Linear algebra is useful. And we decided we wanted to do more linear algebra. Again, once we finally fixed the whole 3 mod 3 equals 3 thing, we could trust the results of the linear algebra it was doing. And they thought that they were going to, go and conquer the HPC space, and they did. It just turns out that if you've ever looked at the market analysis of how much we spend on HPC versus, everything else in computing, it's a single-digit percentage, right? The Department of Energy has a lot of money, but the collective users of Amazon have a lot more money, right? That's sort of the right way of looking at it. And so then at some point, the use that you are probably all familiar with for the last 10 years is figuring out whether or not an image is a cat. You don't actually really need a GPU for that. You can just say yes. We know that all images on the internet are in fact images of cats, right? It's very energy efficient. The It's a Cat predictor requires 0 neurons, no training time. It doesn't even have a particularly terrible accuracy rate. Excuse me. Okay, so if you're looking at how they're used today, as I said, although this is shifting a little bit where you can get more agency out of the GPU, they are still primarily a secondary device where your computation has to start on the CPU. It manages things, dispatches them to the GPU, has the GPU do the work, and then return a result. Right? They're not sharing the same memory system. The GPU physical memory space is disjoint in almost all machines that you would actually buy from the CPU memory system. There is support for things like OpenCAPI, some other sort of high-end server virtualization support for GPUs. That has not settled into its final standard. So if you're interested in that, you can go poke at it and be a part of it. But that's still to some degree an ongoing undertaking in terms of how exactly we want to integrate the GPU memory system with the rest of the system. Okay, so SIMT, right? Here's your old GPU, right? It had a pipeline specifically for, yes.
So I guess when you're implementing these part of the programs, like, can you just like make a whole?
Well, I'll show you some CUDA code. Yeah.
Okay. One thing I was wondering, I guess
I think that'll make more sense when we look at the CUDA program. Do you need a separate programming language for GPUs? No. Do you want a separate programming language for GPUs that allows you to control how you are expressing your parallelism onto the resources the GPU actually has? Yes. So trying to infer very structured data level parallelism from arbitrarily written C, C++, Java, whatever code is much harder than you just telling it, here is how my data parallelism looks. Go and GPU it, right? So yes, a need is too strong a word, but strongly desire, right? We get much better use out of it. If you look at the pre-CUDA era, we had other ways of programming GPUs. They were more hit and miss in terms of what fraction of the resources you ended up using well, right? So there was a period between maybe about 2005 to 2010 where you could get stuff to run on the GPU, but understanding why you got the performance you did was the subject of a lot of postgraduate work, right? And CUDA helped smooth that out a lot. There was a much cleaner mapping between, well, this is the parallelism I asked for, these are the resources I had, and yeah, it kind of looks like I expected it to. So less of a dark art. All right, so we started off, and these things were in fact just graphics processing units, right? So they were concerned about frame buffers and geometry and had special vertex processors, and you know, that's not what they look like anymore, right? So by the 2010s, they pretty much all adapted a model that looked more or less like this. I had a bunch of SMs. These are sort of my notion of a highly internally parallel core, but this is what I'm going to think of as a core in the multiprocessor sense. Right, so these have their own sort of logical structure. We'll get some further breakdown on the next sequence of slides. Each of those had their own sort of local memory. They had fractions distributed of a shared memory. So that's sort of the big scratch pad. So again, think the streaming machines, that heritage coming in there. So while they did have caches, the caches were very small and local. And generally, if they could avoid them, not coherent, at least at the L1, right? If you want to share something, use the shared memory. So it helps with scaling. And then this was a big scratch pad, right? So I could reference other things. Now, it's going to turn out that I don't care how long it takes me really to get access to this data. I care a lot more about the rate at which I can get data to and from that. So GPUs are designed purely as throughput machines. Latency is not the primary design constraint. So I'm happy to have a larger shared memory as long as it sustains the bandwidth that I need. I don't really care about exactly how long it takes to get back. Okay, and we'll see how they hide. We'll see how they hide the latency. There is usually some actual shared L2 cache. There's been a lot of interesting work, as I said, as we start to try to integrate larger and larger memory systems and have more sharing capabilities with the host machine. You start to get questions of, okay, well, what does a TLB for GPUs look like? Again, that's not a solved thing either. So lots of interesting things still going on there. All right. Now, it's not to say that we got rid of all of this, but we got rid of most of this, remapped it into programs that are running here that are emulating what some of this fixed function hardware used to do. There is still some fixed function hardware sitting on your GPU for graphics purposes, right? So as I said, texture buffers in read-only memories to do read-only optimizations on large arrays of pixels, right? There's still some hardware that's especially good at that. You can map computations into using that if you're particularly clever, but you generally prefer not to. There's still particular allocations for sufficient frame buffering and all of the things it needs to communicate with graphics devices. So these aren't all gone. This used to be basically all of your GPU, and now it's some little, special bits of hardware sitting around the periphery. Whereas more and more and more, of these processing units have been stamped out as the GPUs grow. And again, these are somewhat older models, so let's not read too much into it, right? So your consumer hardware by circa 2010 looks something like this, right? I have my multiprocessor here with its cache hierarchy. I have my GPU here with its very differently organized memory hierarchy, and they are completely disjoint memory spaces. And so one of the challenges in using the GPU was always, as a computational device, was having enough work to bother notifying it that you wanted it to do anything at all, right? So if I got to walk all the way from here, right? This takes a while. That's a technical term, right? Again, microseconds on the PCI here. And again, because this also did not have a lot of independent agency, right? This couldn't even ask you for stuff if it didn't have it, right? So you had to actually send the entirety of everything this was going to need over. And then all you would know is that when it was done, you'd get an inappropriate interrupt to go grab the result, right? Like any other IO device, right? So here you had a device that increasingly had more transistors than this, right? Teraflops of computational power, and you still treated it like the family dog, right? So, you know, details. Okay, so what are they good for? So let's decode some of these things in this slide. Unlike a vector processor, there's no scalar processor. It's all data parallel processing all the way down. We'll talk about the multi-threading to hide latency in a second. When they say large register files, here's what I need you to start to get into your mind. When you think about a CPU, your register file, your architectural register file is on the order of like a kilobyte, right? 32 by 32 or 32 by 64, it's a couple of kilobytes. Your physical register file is larger, right? Because maybe you have actually 300 registers, not 32. Your physical register file you have on a machine. But okay, so let's make it 10 times larger. 20 kilobytes. No. This is like a meg. Right? When we say large register file, we mean really, 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 really large register files. And the reason is going to relate actually to this. We are going to keep a very large number of contexts live. Right? So the other thing that comes back into our GPUs, think back way back to the in-order portion of this semester and fine-grained multi-threading. So GPUs actually use something that looks a lot like fine-grained multi-threading. So you have a vector thread style parallelism of issuing an instruction across an array of lanes, right? These virtual processor cores. And then in the very next cycle, you're going to do the same, but from a different set of threads, right? So you need to actually keep all of these in context, right? So huge register files. So it's pretty reasonable to expect, 32, 48, 64 warps. A warp is that collection of threads that are all executing the same instruction are there at the multi-threading level. So very, very, very heavily multi-threaded. So again, not designed for latency, designed for throughput. Right? They're going to be highly tolerant. Right? So I might have 48 other threads, 48 other warps, come between me and coming back to get my data. So if it takes a while to get it from the other side of the chip, it's not going to be a huge problem. They still support a lot of the things that are there from vector processors, right? You do still have mask registers. You do still have support for scatter-gather. But the scatter-gather latencies, again, can be hidden pretty well here. at least to a first order. And they're still going to really work well with data level parallel problems. If I do not have a data level parallel problem, it becomes very difficult to get my GPU to extract a lot of performance from it. Right? So again, think about where it's getting its internal parallelism in pretending it's a vector processor, even though all these things can actually independently diverge as threads. Divergence is bad, right? Not just the movie series, which was bad, but divergence, the concept, is bad, right? If, only one of my threads went one way out of the 32 that I issued the same instruction to, well, I lost my 32x parallelism and I now have 1x parallelism, which is not so great, right? Okay, so let's zoom in a bit. Right. So in practice, if you break down the memory system as well, we start optimizing for bandwidth. You are going to very, very heavily bank everything. Yes, this is old. This is GDR3. Does the GDR6 version look the same? Yes. At the block diagram level, change the number, right? Doesn't matter. So lots and lots and lots and lots and lots of banks of controllers, right? Again, I need to maximize my bandwidth. I'm more concerned with that than my particular latencies of dispatching to one of these memory controllers based on my physical address, right? Moreover, I don't really worry too much about missing out of my physical memory. I don't have a paging problem with my GPUs if I'm operating them in a fairly traditional mode, because the CPU set up the entire memory image and then that's all you got, right? Again, as we start to look at aggressive virtualization within GPUs, eventually you'll have to worry about paging, direct device access, those sorts of things from the GPU space as well. There actually has been some interesting work on trying to take the CPU out of the loop for things where, say, for instance, a GPU is doing processing on graph data on an SSD, right? If you can get the CPU out of that whole interaction, it can speed things up a lot. Okay, so these are all of the processing lanes. So there are a very, very large number of lanes in this vector processor style. Right, so again, remember that there are a couple different ways you could do vector processing. Right, I could have one ALU and it's going to process all the elements of vector sequentially. I also have the dimension of stretching it out and doing a set of lanes to do them in parallel. In GPUs, it's all in the parallel space, right? Because I want to treat each of these processing lanes as if it's a scalar processor, right? I want to treat each of these as if it's a one wide 48 to 64 threaded FGMT processor that just happens to most of the time be executing the exact same instruction as its 31 or 63 closest friends, right? So again, we're doing a hardware control, and here's a nice size register file, 32,000 registers. It's a reasonable register file. They've gotten bigger, right? Yeah. Now, you do have your sort of dedicated load store units. You do have special functional units. These are not provisioned to the same degree as these, right? These are, right? The matching number of these to these. These are not. So if I want to do cosine on my GPU, it will be slower. I do not actually have, 32 or 64 cosine units. I do not have 32 or 64 logarithmic, whatever complex function I'm doing here. If you're looking at places where, I won't say the model breaks down, but you can see some of the limitations of how these are designed, you can run out of specialized functional units. You get contention for those. It will run slower, right? Will it bog down and not be worth running on the GPU? No, it's still probably a lot better. But you don't want to do a computation that is nothing but trigonometric functions on your GPU, because that's not what it's designed for. It's designed for linear algebra, and linear algebra mostly looks like adding and multiplying. If you want to add and multiply, GPUs love you. If you want to add and multiply over enormous matrices, because what is an image, right, except an enormous matrix, right? They're very happy, right? You want to do complex trigonometric functions? No, they'll do them, but it'll be a little slower. It'll be a little slower. Okay. So bunch of PCs, some mask bits, do have instruction caching. Their lack of love for caches is pretty much only on the data side. This makes a lot of sense. The kernels that they are running are not usually very big, right? So an instruction cache works just fine, right? Your hit rate there is going to be very, 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 very high. Okay. You do need to decode them into some set of actual instructions to execute, but then they get dispatched with the masks to everything. Okay. And again, most of the time you're not worrying too much about the masks, but it's gonna handle this in hardware, right? You don't have to actually do the algebra of predication yourself in the compiler. The hardware will determine dynamically which things actually went which way. It will reformulate with the thread schedulers, right? Which are actually sort of warp. These are called warp. Well, pause. None of the different people who built GPUs could originally agree on exactly what everything was called. I will be using primarily NVIDIA specific terminology, but without loss of generality. The collection of things I want to all happen at the same time across all the lanes is a warp. Right. So anyway, so there's lots of stuff in the warp scheduling itself about understanding which of them I should schedule. You could even, if you wanted to, have two warps, both of which ended in branches, right? But they were logically the same branch, and half of them went one way and half of them went the other. I could re-swizzle those into two warps, all of which went one way and all of which went the other rather than four. Does it actually do that? Pick your generation. People have certainly proposed it. Okay. So what are some of the things that you actually then want if you're going to talk to these GPUs, want to express a computation onto it? So we'll come back to, where did he go? Well, we'll come back to that question potentially if he comes back. Okay. So let's say you've defined a few things here. You do need synchronization intrinsics. Again, you don't want to write your own for CPUs. You definitely don't want to write your own for the GPU side. But CUDA code starts to look at things that look sort of like this, which is going to be a parameterized dispatch of some function. This function is basically the kernel is going to execute. These are some of the parameters. This is what it's going to look like basically from the side that is calling it. So I'm going to walk you through some examples here. So your CUDA code, the first thing you're going to notice is that there are a lot fewer loops, right? Because what you're going to do is you're going to turn a number of the loops into parameters of the function, right? It's not that your CUDA code can't have loops. It's just that unless it's pretty deeply nested, you don't need them, right? So again, think of it this way. If I have for I equals 1 to 10, for j equals 1 to 10, there are only 100 things to do. And the GPU way of doing that would be unroll everything. I don't actually unroll everything. I unroll everything at a compiler level by parameterizing what it is that you've asked me to do. Basically, the inner loop is the actual place all the code is, right? Everything else is just on what should I execute this, right? So anything I can express as data level parallelism for all these data elements, do this, right? I'm going to try to unroll that all the way down because I've got a very, very large number of pieces of hardware that could do the work if only you could get the operands there, right? And again, to get a sense of how many pieces of hardware we're looking at, and also to make sense of NVIDIA marketing terms about the number of quote unquote processors that it has on its chip. Without loss of generality, we'll stick to powers of 2. Let's say that you have 64 SMs, and each of these SMs can do 64 lanes. Then what they're really saying is I basically got a 64 core processor, each of which is 64 SIMT wide, for, last I checked, a 4096 way parallelism. But wait, right? That's at a time, but in terms of what I schedule, I might then also have 32 threading, right? So this is how much I can do at a time, but I'm going to schedule 32x that much work, right? And then hide the latency behind the multi-threading at this level. So the total number of quote unquote threads that they say that they're going to have is multiply all three of these numbers together. The actual parallelism is this number. And so you start seeing numbers that are 4,000, 10,000, 12,000, right? Those are looking at basically the number of ALUs, right? Or equivalently, the number of SIMD lanes across the entire chip, right? So if you look at the most modern largest ones, this number is higher. This number is pretty much fixed. This number is higher. So you can get there to your 10,000, 12,000, et cetera, for your 4,096. Sorry, 4090, if you're looking at the tech specs. Anyway, so if you look at what CUDA code is going to turn into, is basically you're going to define the work to do in terms of the parameters that specified what data to do it on. Right? And again, in this case, if I only have one loop, I'm almost certainly going to basically unroll the whole thing, at least logically, right? Even if I'm chopping this up into different pieces and distributing it where there still is some higher level loop. From the perspective of the CUDA code, it doesn't have to know that, right? I just want to talk about what does one individual SIMD lane have to do. And all it has to do is figure out the particular element. These will be compile time constants. They'll get compiled away. And then do this work, right? So if I want to add A of I and B of I into C of I, right? The only thing I care about is this part. And all this is going to be taken care of at compile time to dispatch the right data to the right lane. Right. Now you can also see why if you don't have structured data level parallelism, this is not going to help you much. If you can't express for every data item, here's what I want to do to it, right? Then that is not the CUDA way. So let's look at something with a little more structure. So let's say I want to add two matrices together. The natural way to do that in C would be something like this. I've got a matrix of excuse me. Got a matrix of floats C. I've got a matrix of floats A and B, right? And I am going to have C be set to the sum of A and B. So just for I less than n, for j less than n, I compute my index within this matrix, right? And then I say C of index is A of index plus B of index. Would you actually necessarily do this immediate step here, or would you just do two-dimensional indexing? Up to you, right? But 6 and 1, half dozen of the other. But in the CUDA version, you really would do something that looks a little more like this. This makes more sense. So you'll note, right? Int main add matrix done. Here, int main figure out how I'm chunking the matrix into pieces that are going to be worked on, right? And then dispatch this function across all of those chunks. And if you look at the actual function, look, no loops. Right? Because all it's actually going to do, right, is just check that it's in bounds and then do it. The inbounds there having to do with the chunking that had occurred. Okay. So we're basically going to desire, right, that we have this stupidly large number of threads. Now, when we say stupidly large number of threads, these are not the threads that your operating system schedules, right? These are basically the work on some data parallel SIMD lane. So they need their register state, right? They do have a context, but that context does not get preempted, right? And the thread is not doing sort of random arbitrary stuff. With concurrency, these threads are almost always parallel, right? So the management of a very large number of threads doing exactly the same thing is easier than a very large number of threads doing who knows what, right? Right? The edge cases in particular are drastically easier to handle, right? And the GPU hardware handles all of this thread management and thread scheduling, right? So I will allocate 32 warps to each of these 64 SMs. If my problem is big enough, my problem is not big enough, I won't use them all, right? Just like if you have a program and it's only four-way multi-threaded and you run it on your 16-core machine, that's not the machine's problem, that you just didn't give enough work to do, right? So same thing here. right? So up to 32 warps onto up to 64 SMs, right? And then each of those SMs, 32, 64, however many particular lanes it has, that's going to be scheduling. That's the width of a single warp, right? That's the work it's doing. And then interleaving among those threads for latency tolerance, right? So you may only have, right? Again, it's a pretty short pipeline, right? This is a short in order pipeline. Right? So this almost looks just like FGMT, except that it's FGMT only if you zoomed in so far you don't see the other SIMT lanes, right? Because it's FGMT at the warp level, not the thread level. There's a notion of the blocking of memory, right? Context thread, I can remember what all the acronyms stand for. And again, NVIDIA and AMD don't use the same ones, but this is just the number of different collections of where the warps are going to be coming from. The width of each of these blocks is based on the number of lanes that you have. Again, you don't have to know this, right? CUDA will abstract this. So one GPU to another GPU to another GPU, these internal parameters might be different. That level you don't have to understand. So you don't have to understand whether you have 64 SMs or 96, right? I get your 4090 and your, 2080, right, can run the same code, right? Whether it's 64 wide, 32 wide, again, you don't have to know that. Whether it's 32-way multi-threaded or 64-way, you don't have to know that either. That's all handled in hardware. Right, so it's doing a bunch of hardware thread scheduling, warp scheduling. Right, this is all happening deep down in the hardware under the hood. Right, and again, because they are not doing arbitrary concurrent computation, I don't need to have an entire operating system worth of understanding and priority. I'm just like, no, which of these is ready? Then do it. Right, it's not super complicated. Everything else is an optimization. Right, correctness is not their problem. It's just performance. Okay, so I have an application. I run it on my host CPU because history. I have to push it across a set of device APIs that still thinks it's actually a graphics processor and not a enormously super powered high performance computing machine, right? And then I basically develop a work queue of kernels, right? So the unit of scheduling from the CPU to the GPU is called a kernel, right? You can think of it as a function. This really just has to do with defining a set of data and the function on it, right? That's the two pieces that you're looking at for a kernel. And then I schedule some set of these to be done. They have their own set of internal dependencies. GPUs do not generally support kernel preemption. Once I schedule a kernel, it is going to run until it is done. Right? I can get lots of reordering among different kernels that have not started running yet. Right? I can get, in more modern GPUs, some virtualization of resources where I could have half the GPU be working on one kernel, half the GPU working on another, right? Possibly from an entirely different application, right? Certainly if you're doing this in the cloud, you want to schedule as many different things for as many different people as possible to keep everything occupied, right? Utilization is money. But once it's scheduled, it's going to run to completion, right? Now, this is the software side interface of the GPU. Once you actually push a kernel to try to schedule it, the GPU has to understand how to map that kernel into the physical resources that are actually on the GPU. This is where these things here matter. So these are still abstracted, right? Once you have a collection of warps where you've carved up all the work to do into SIMD-like chunks of however many lanes you have, then you have a warp scheduler that is going to rotate them through. This is basically your multi-threading level FGMT scheduler, but across some number of vector lanes, right, for each of your SMs, right? And now, of course, they still have dynamic behavior, right? You don't know in advance exactly what's going to happen. There are still branches, there's still cache misses, right? And in particular, right, the model, the SIMT model right? Everything is technically a thread, but it works well when it looks like SIMD. So just like with SIMD, while SIMD can handle branches going different ways, it doesn't like that. Well, it can handle some things having cache misses and some things not, i.e. variable memory latency, variable progress across all the instructions within a single warp, right? It does not like that, right? That comes back and makes the scheduler sad and says, what do you mean only half your warp is ready? No, I'm waiting for all of you. Right? Or it has a more complicated version and recompiles the whole thing, but generally not, okay? Again, this is NVIDIA speak, right? Where does warp come from? Not from warp speed, but from warp and weave, right? Textiles. Lots of computing can trace itself back to Jacquard loom and punch cards and all that, right? Anyway, don't ask where all the names come from. You don't always get great answers. The answer is, in fact, it came from weaving. Okay, these are all running the same kernel. They're all running, in fact, on the same block, right? And they have an ID. So if this machine was a 16-lane machine, right, then it would basically be using that in hardware to understand which data element this particular thread is working on. So it has some lane local knowledge, so it works on the right data. Right. The pipeline is pretty simple. Fetch, decode, take a while to go access the 32,000 element register file. Do some work, possibly access a cache, and then right back. Right. So again, it's like you had a simple in-order FGMT machine, except really stupidly wide. Okay. So no S context switching. Register values means that everything has to stay in the register file, right? So that's why that's so big. In practice, it utilize all of the resources because they run out of register space, or they run out of shared memory, or they run out of some other finite resource. So GPUs are in practice actually frequently underutilized, not at the level of individual warps. When I usually express problems where I can find at least 32 or 64-way parallelism, or else why am I bothering with the GPU? But in terms of using all of the SMs, so these are all sharing access to that 32,000 register file. And if each individual thread needs more registers to store the total thread local context that is not being switched out, maybe I only end up using 50 of these because I just ran out of registers, right? But the compiler will figure that out, right? You again don't have to figure that out at the CUDA level. Now, if you're wondering why everyone was so happy with CUDA, before CUDA, you had to figure that out. Right? So before CUDA, a lot of this was very naked if you wanted to actually understand the performance you were getting. Like, oh, you write your program to fit exactly the resources of this machine, right? And again, in the early days of this was not the end of the world because the only people who were trying to do anything with GPUs were HPC people who were used to rewriting all their code anyway for every new supercomputer that came out because they didn't even trust the. There's a fun story from one of our faculty members who has spent some time working in a national lab where they didn't trust the compiler. They're like, look, we've been working on this same kernel for 15 years. I know what it's supposed to do. I know what resources it needs. I'm going to schedule this myself. I know better. Go away. And they did. They were right because that's literally what they did. They just took this one particular kernel and then mapped it to progressively more powerful machines, and they had been doing that for 15 years. And the generalities of the compiler optimizations had not caught up for their specific case. Right. So, but obviously, most of us don't want to spend our entire career working on one particular formulation of sparse matrix vector multiplication. I'm not saying that's a bad thing if you do. Anything that has to do with sparse linear algebra is still awesome if you can make some gains on it. But for the rest of us, there's CUDA. Right? Okay. So as I've mentioned, the ISA doesn't actually understand that it's part of a warp. Right? The ISA thinks it's a scalar ISA. This is the trick of SIMT. Right? The hardware scheduler is scheduling a bunch of SIMD operations. But the ISA level for each of these individual lanes is operating under the illusion that it is in fact a one wide scalar processor with one thread, and there's no one else in the world that it ever has to worry about. Right? This is how divergence is handled. This is why basically the GPUs put the final nail in the coffin of any vector processor, because everyone was much happier to have hardware figure out all the vectorization as it was occurring than to actually go and figure out whether they should be predicating, whether they should be dropping back to scalar, whether it's like, no, we're just going to let each individual lane believe it's an independent thread, but without all the threading overhead of a real multiprocessor scheduler. Right? So the programming model technically is SPMD, right, like a multiprocessor, but really it only works when it's SIMD. Okay. So again, to take home where it breaks down, if you have irregular memory access, GPUs get cranky. Now, GPUs can still handle this a lot better than your CPUs, but that's all because of this, not because of this. So if I want to walk a graph, I will still use a GPU. Right? People will still do graph problems on GPUs, but the type of parallelism that they're looking for is very different. Right? The expectation is my memory behavior will be fairly bad. I'll get a lot of divergence. But if I can have a large number of concurrent queries, I can still map that into my GPU model and it'll still be better than my CPU model, because my GPUs are actually designed to handle a very large number of outstanding misses, because they're a throughput machine, not a latency machine, and they have enormous amounts of multi-threading to help hide some of the latency that I'm going to get on those walks through pointer-based structures. But compared to dense linear algebra, the performance of GPUs on graphs is trash. Right? So the fact that it's still beating your CPU is not a deep statement, right? But it's grossly underutilized. They don't like irregular memory accesses. Divergent control flow. So the good news is you didn't have to have the compiler figure out the mask registers, do the predication for you. The bad news is if half of your threads went one way and half of your threads went with the other, I have probably lost half my parallelism. Right? So the way that scheduler is going to work is it's going to dynamically split that warp into two warps, one that went one way, one that went the other, and schedule them independently now. But each of them is half as big. Right? It'll fix that. It'll do that for you. It removed the management overhead. It removed the instruction fetch overheads of doing that by doing it on hardware. It doesn't make all of your branches go one way. So if control flow diverges, bad. Memory diverges, bad. You want to do trig instead of linear algebra? Well, I didn't provision enough, so good luck with that. Right? If I need a lot of registers for every one of my threads, no, that's not so good either. I will run out of resources. That is a frequent thing that I actually run out of. So all of the above, these are all the challenges in SIMT in practice, right? All of which have relationships to the challenges in designing a good vector processor that manifests slightly differently. Right? Vector processors also had enormous register files, right? But because the SIMD was explicit, right, you sized it accordingly, right? Whereas here, the SIMD is hidden, and so which resource you run out of first might change, right? But same problem in scaling. Right. This, I think technically was a problem in vector processors as well, but was not usually the first thing you ran into, because usually your vector processor ran aground on these well before it hit C. And indeed, actually the case for GPUs as well. These two are in fact the biggest impediments to high utilization. Right. So again, on a throughput machine, what do you want to maximize? Utilization. If my goal is work per unit time, I have lots of things that could be doing work, keep them occupied with something, right? If I have divergent control flow, that means only a fraction of my units could be occupied because the others didn't go that way. I've lost utilization. This is actually one of the reasons why, if you look at more modern machines, one of the things that they've actually done is say, well, actually, we don't necessarily have to have 64 lanes. What we can actually have is a partitionable, right? Maybe this is actually, like 4 by 16, right? So I actually have 4 partitions of 16, and I can schedule at a finer granularity, right? And then in the case where I have divergence, right, I could still actually not lose quite as much of my utilization. I have finer grain control, but again, comes with a little bit of overhead. And where will I claim, and we'll I'll get into this a little more on Thursday. A lot of the benefits ultimately were realized. I mean, the model is good, don't get me wrong. But the enormous benefits that GPUs have been able to achieve have actually come from the energy per operation benefits you get from adopting this model. Right? So once we became power constrained, right, it wasn't just that this was a good way of expressing parallel programs, which it is, if by parallel you mean data parallel, but it also, by virtue of using very large numbers of very, very simple pipelines, and then getting all of its performance out of the parallelism rather than hardware intelligence, right? The only intelligent piece here is your thread scheduler, your warp scheduler. You were able to get a lot more bang for your buck than CPUs were getting out of going wide in out-of-order execution. And we'll see why that was so important when we again revisit our favorite topic of physics hating us. Okay. So the one final thing I will note, which just fell completely out of my head. Isn't that important? Well, either it'll come to me and I'll mention it on Thursday or not. Warp scheduling. No, I think we're good. Yes.
So does SIMT kind of like function like somewhere like logically the way like the HLS unknown fragment does?
Yeah, but it's a little more flexible. So the HLS unroll will get you SIMD. Right? HLS unroll will get you SIMD in terms of the hardware. And so here, you can really think of this as a hardware virtualized approach to pretend to have massive multi-threading, but in reality really just have a more flexible SIMD processor. Yeah. So, but yeah, if you're looking at HLS unrolls, will just actually give you a SIMD unit. If you wanted to have them be flexible enough to handle divergence, I don't know of any HLS tools that can understand how to build that in naturally from just the expression of an unrolling. Yeah. Okay. I think you had an earlier question as well, but you, yeah. Do you remember what your earlier question was?
Let's say I have a portrait application, but like, it's not like I'm writing for application.
Right. So here's the example, right? So you're basically going to break it down into the chunks that each kernel is going to work on. It's parameterized. This dispatches all, for every dim grid and dim block that exists. This is going to dispatch a kernel to work on it. And then this basically has gotten rid of the whole loop structure. This is just basically turning it into a mask to make sure that when this maps down to the particulars of the ID space, that it's still actually in bounds. And then this has basically been dynamically unrolled into a series of compile time constants plus, where are you? Sent into software work queues, one kernel at a time, kernels have no preemption. Where are we? And then you have local variables that actually let you know how to interpret which data element you're actually operating on as a function of which lane you actually are in. Yep.
Then you get to the part where you use like the
Yep.
video or something. Like, how do you actually invoke that? Like, in your code?
Like,
It's not like you're just gonna have. Oh, that's.
yeah, that's literally it. That's CUDA invocation.
Okay.
Yep.
That kind of thing.
Right. So here is I define a CUDA function kernel, and then I dispatch it across a pile of data. Yeah. They're a set of hooks. Yeah. Okay. Any other questions? No, I will see you Thursday.
So is